Welcome to this NPTEL course on Advanced Pre-Stressed Concrete Design. We are starting a new module, Module 9 and Part 1. In this module, we are going to talk about the importance of Strut-and-tie model, what are the basic concepts of Strut-and-tie model, and how it can be used for understanding the structural behavior, and what are the methods for formulating the Strut-and-tie models. So, the expected learning outcomes after the student goes through the video, he or she will be able to understand the importance of Strut-and-tie model in designing the disturbed regions and understanding the basic concepts and structural behavior of the Strut-and-tie model, and to gain knowledge on methods for formulating Strut-and-tie model. So, for the same load requirement, for the same geometry, one can come up with different configurations of Strut-and-tie model, still can design a safe design. So, let us see what are the do's and don'ts in formulating the Strut-and-tie model. Now, why we need Strut-and-tie model? You can see that typically for section analysis is what used by the engineers to calculate the capacities. So, typically in a structure like what it is shown here, a portal frame, you have several point load regions that are highlighted here. So, for example, you have some point load that is in the midspan of the beam, then you have a corbel, right? And the corbel, typically your gantry grain will run, let us say, in an industrial structure like this, a portal frame will have a corbel through which the gantry grain will be running, and that will induce the concentrated load. Then when you have a dapped in connection, again the reaction will be putting stress concentrations and it will be creating a local regions or disturbed regions. So, there are usually two types of regions, as we have said, main or B regions. B regions are also called as Bernoulli's regions, where we can assume that the strain distribution is linear and we can use sectional analysis for calculating the capacities. But in the local or D regions or disturbed regions, your Bernoulli's strain assumption is not really valid, and we need to use specialized models like Strut-and-tie model for calculating the capacities. So, the local regions, typically they will include the ends of the column or a beam, where what we have seen here, right, and the corbels, that what we have shown here, or a region that is very adjacent to the concentrated load like this, and typically it extends by a distance of d effective depth on either side of this load. So, these are the disturbed regions or D regions, where there is a lot of stress concentration as well, because it is subjected to heavy concentrated load over a small region. Now, how do we understand the behavior? The structural behavior of main or B regions, you can see that this is a region in which the plane sections assumption, the plane sections remain plane, is really valid. That flexural theory, they can be applied with linear variation of strain. In all other regions, disturbed regions, this assumption is not really valid, right. So, this is the example of a beam. For example, simply supported beam, when it is subjected, we know that if you take the cross section and you find the strain variation, it is assumed to be linear, and it is perfectly valid for relatively slender beams when it is subjected to uniformly distributed load. This is a very good assumption. So, even for a slender beam, close to the regions where concentrated loads are applied, in strict sense, this Bernoulli's hypothesis or the strain variation linear is not really correct. Now, what is the structural behavior of local or D regions? D regions, as I have told you, these are called disturbed or discontinuity regions, and these are the portion of the member where the strain profile is significantly non-linear. So, the D regions, wherever the D regions can come, the D regions can be at the locations where there is a geometric discontinuity. It can form close to where you have openings or holes in, for example, in a beam, typically opening is created to facilitate the mechanical, electrical and plumbing provisions, and wherever there is an abrupt change in cross section, also you can have D region, or wherever you have statical discontinuities, where externally there are some concentrated forces come, then that regions also disturbed regions. And typically this is near the concentrated loads and reactions. Now again, as you can see in a deep beam, deep beams depending upon your A by D ratio, as you know, typically A, this is your D, right. So typically when your A by D ratio is less than 2, 2 or 2.5, we call that beam behavior as a deep beam behavior. Then your strain variation is not really linear, you can see here it is basically a non-linear strain variation like this, right. And also if you have a beam like this with a depth end, and if it is supported and it is subjected to uniformly distributed load, if that beam also has a hole like this, right, in this regions you form disturbed regions. For example, that's what we said, closed from the support up to the depth of D of the beam, you will have disturbed regions on either side. Then close to the hole, away from there, again you will have a disturbed region, right. All those regions, until the width of the hole on either side you will have disturbed regions. But for easy facilitating top and bottom of the region, we assume that it is going to act like a Bernoulli region. So you can see that wherever there are some discontinuities, either in the form of a geometry or in the form of a heavy concentrated load, those regions will have disturbed regions where your Bernoulli's strain variation linearity is not really valid in strict sense. Now let's look at it. These are some samples that or the finite element analysis elastic stress contours that we have taken. You can see for a corbel which is subjected to heavy concentrated load, you can see these contours are basically tension field contours. So now you can see that the tension is developing like this, then you have a tension like this, then you also have a tension that it is coming here. So you need to really model this like a tension region. So similarly you can see that the force flow is coming like this, right. These are all the locations. We need to assume some ties. So this red color is basically where the ties. These are all the regions. Definitely you need to have some ties, right. So on these regions connectingly you can have strut, right. So like this we can form. Now how about the compression stress field? As we can see here, for the same beam, now as I told you, compression stress field is going to go like this, right. In addition to that, you also have compressive stresses that are developed like this, right. So these are the regions that compressive stresses are getting developed, and you form here you can find that compressive stresses are going to be developed like this. So you have to do some elastic stress analysis to find out the principal stress contours, and the struts will usually form along the principal stress compressive stress trajectory, and the ties will be assumed to form along the principal tensile stress trajectory. Now what is the importance of strut-and-tie model? It can help in the design of this local regions, where again we cannot really apply this Bernoulli's hypothesis, and the local regions are typically designed based on experience or empirical rules or rules of thumb. Okay. Now strut-and-tie model, it is actually a valuable tool for helping with analysis and design of a concrete member, and particularly for regions where plane sections assumption or beam theory is not valid and strain profile is significantly nonlinear. So now let's see how do we do that. So in STM, let's look at the basic description. In strut-and-tie model, they involve idealization of a complex structural member into a collection of compression member, strut and tension member ties. And usually, for example, this is a very simple strut-and-tie model that one can think of. You have a huge concentrated load that it is acting, and you have these support reactions. Depending upon the width you can form. So you have basically three main components that are there in the strut-and-tie model, where compression struts form, they help to transfer the compression force, and the tension ties are assumed to form, that is help to transfer the tension forces, and nodes are something like a connections region that what we have in steel structure design. You have in steel truss bridges also, you have compression elements, tension element, and they are all connected by some connective elements, right. So, in the same way, nodes are the regions where these intersections of the forces are all properly designed to be transferred. So, for example, very simple example that we have seen for this deep beam, and you can see that a strut will be forming to transfer this applied load in this form. Basically, the simple truss has to force the flow into the support like this, right. So, that is why we have put like this, it has to take the load. Similarly, to balance this, I need to also develop some ties, right, because if I look at the force equilibrium, horizontal force equilibrium, then there should be an element that will be subjected to tension. So, that is a tie element, right. So, and then in the connection region we have nodes. So, these are all the nodes that what we see are the compression and tension elements, they go and join together, right. Now, you see here that whatever that these regions are in strict sense, this concrete is not really used. Not really used for load transfer. So, we are assuming that there is going to be a truss forming inside the beam that is going to help in transferring the forces. So, strut, which is a compression element, a tie, which is a tension element, and the node regions where the compression struts and ties will join together. So, we have to make sure that the struts are designed adequately, ties are designed adequately, even the node regions have to be designed adequately, otherwise they can also fail and lead to collapse of the structure. Now, what are the assumptions? And Strut-and-tie model is a lower bound method. That means it is going to give you the predictions of the capacity in a conservative way, and typically, again, as we explained, they are used to design discontinuity regions based on plasticity theory, provided the following conditions are satisfied. What are those conditions? Equilibrium condition. Again, all the models has to satisfy equilibrium condition. So, whatever the configurations of strut and tie that we choose, they should always satisfy equilibrium. You cannot violate equilibrium condition. And the yielding of tie is also assumed to occur before the crushing of the strut. Again, this is a desired failure mechanism, because if concrete strut is going to fail, it is going to be a very brittle mode of failure. So, we always want the ties to be yielding, that will help in ensuring the ductile behavior. Now, reinforcement, again, the ties should be properly anchored. So, if the ties are not properly anchored, into the support region, then you can have premature failure. So, even though you might have provided adequate number of area of steel, but if they are not anchored well, then it may lead to premature failure. So, the reinforcement should be provided with sufficient anchorage. And the external loads, we are saying that they will be applied only at the nodes, and the pre-stressing is treated as an applied load only. In this method, this is how we are going to assume. And forces within struts and ties are considered uniaxial, and tension in the concrete is neglected. So, just like truss. So, the struts, ties, everything will be subjected to uniaxial forces, and concrete contribution in tension is neglected. Of course, if you are using fiber reinforced concrete with lot of fibers, then your assumptions have to be slightly modified, and also the efficiency factors for strut and the ties will also improve significantly, that we need to be careful about. Again, even though you use fibers, maybe the ultimate strength will slightly get altered, but the influence of fibers, the moment we are looking at it, the ultimate, the Strut-and-tie model, we are trying to calculate the capacities at the ultimate condition. At that time, again, if the crack widths are larger, the contributions of the fiber may not be that significant. So, we need to appropriately include the effect of fibers depending upon the dosage and the characteristics of the fibers that you are adding to the concrete. Now, what are the key concepts of the struts? So, now let us look at all the individual components of the strut-and-tie model. Now, what are the key concepts of struts? And as you have seen, the struts represent the concrete compressive stress fields with the compressive stress acting parallel to the strut, right. So, we are saying that along the direction of the strut is where the compressive stress flow is going to be. Now, the struts, they can be prismatic, that means the cross section of the strut is not going to change, or they can be uniformly tapered, that means the width of the strut can taper, or they can vary in the cross section along their length. Okay. So, because the concrete stress fields are wider at mid length of the strut than at the ends. So, we can typically we have three types of struts. One is a prismatic strut. We can see, either you take here or here, the cross section remains the same. Such type of struts are called prismatic strut. The second one is called fan shaped strut. You can see that the cross section is actually tapering out, right. So, it is tapering out, it is increasing in the fan shaped. And the third one is a bottle shaped strut, where you can see it is forming in the form of it is varying in the cross sections here, it is varying. So, this kind of a shaped strut is called bottle shaped strut. Now, let us understand the failure mechanism of struts. Now, the strut failure usually happens by longitudinal cracking in a deep beam. So, if you take the free body diagram of a deep beam which is subjected to loading like this, and we say that the strut is going to form like this in a bottle shaped configuration like this, right. And this is the width of the node. Typically, it corresponds to the width of the loading plate. Then, based on the geometry, we can arrive at the geometry of the nodes and the shape of the strut as well. Now, if you see here, there is going to be compressive stresses that will be transferred. Now, because it is going to be compressive stresses along the strut direction, now in the perpendicular orthogonal direction, I am going to develop some tensile stresses. Now, at certain point of time, these tensile stresses will exceed the tensile strength of the concrete, and it will have a crack like this. It will have a crack like this. So, you can have, though the strut is formed, the strut can actually split because of the transverse tensile stresses which are happening in the perpendicular direction to the direction of your strut. Now, again, the strut failure by longitudinal cracking is very common, that we have also studied in the anchorage zone design, right. The design of disturbed regions where you post tension anchorages are placed. We have seen that when you have such kind of an anchorage system and you apply the pre-stress P0, we have seen that for a distance which is equal to depth y0, you will have this kind of stress distribution, and you will have, for example, when the stress becomes uniform, that is the region beyond which we can use Bernoulli's hypothesis. So, basically we say that this is how the stress, right. We are going to design this like a deep beam, that is what we saw in the previous lectures. And the transverse tensile stresses, we have seen that it will develop after 10% of this y0, 0.1 y0, and this is the region where your high transverse tensile stresses will develop, right. So, we have seen that. So, here we need to put some reinforcement which is in the longitudinal direction, in the vertical direction, that will help me to resist this transverse tensile stresses. So, if you see here, this is how it is going to come. Then we try to put this reinforcement. If it is going to crack like this, I need to put reinforcement like this, right. So, that is what we put this kind of a mat type reinforcement that will help in preventing the cracking from this transverse tensile stress. At the same time, the reinforcement in the vertical direction is going to help me in strengthening that strut that it is forming in the direction, right. So, this is how we see it. Now, the failure mechanism of the strut, you can see that compression failure of the strut, if adequate transverse reinforcement is provided in the strut, then the strength of the strut will be governed by crushing of the concrete. just like in columns, right? In columns, typically we provide ties to confine the core. So basically this transverse reinforcement also helps in confining the strut. Okay. According to ACA code section A3.2, the crushing of the strength concrete in a strut is referred to as effective compressive strength. So there is a factor, let us say FC is your cylinder compressive strength, then there is an efficiency factor that it is given that typically varies from 0 to 1. Okay. Now, if I put more reinforcement in the transverse direction to the strut, then the efficiency of the strut will go up, right. So, if you want to have more strength contribution from the strut, so you have to put some reinforcement in the perpendicular direction to the strut. That will help in delaying the crushing of the concrete and spalling along the strut direction. Okay. So, this is, you imagine this like a column, basically strut is basically like a column that it is forming within the beam, and the columns usually we provide confining reinforcement the same way. If you put confinement reinforcement, that will help in ductility and improving the efficiency of the strut. Now, key concept of ties. Now, let us look at what are the concepts of ties. Now, ties, as we have explained, they serve to resist the tensile stresses which are generated by applied loads, and that helps to transfer the forces between the nodes, and they also help to balance the compression delivered by the strut, right. So, whenever you have an inclined compressive component, you have to satisfy the horizontal equilibrium, you need to have ties in the node regions, right. So, in the reinforced concrete strut-and-tie applications, ties are usually composed of steel reinforcement or pre-stressing stand, and they are intentionally placed to withstand tension forces and to anchor the compression struts effectively. As I have told you, again the ties have to be adequately anchored, otherwise it can lead to bond failure and the efficiency of the ties will be compromised, right. So, we need to have adequate anchorage. This is what we said, you have a strut, and to maintain this horizontal equilibrium, so you need to have tie like this. But this again, these ties have to be really anchored well, then only the efficiency of the tie will be quite good. Okay. So, now again the ties, the concrete in tie typically is concrete, just like we do in regular analysis, concrete tensile strength is usually ignored. So, concrete in the tie region also, we assume that it is not going to help in resisting any load. It only aids in the transfer of the loads from struts to ties or to the bearing areas through bond with the reinforcement, just like what we do in your simple bending theory as well. Though you have concrete below the neutral axis, we do not consider them in our ultimate strength calculations. The purpose of that concrete is only to help in transferring the stresses through bond. Now, the concrete surrounding the tie steel, it helps in increasing the axial stiffness of the tie by a phenomena called tension stiffening, because at the crack location concrete does not contribute. However, between the cracks, you know that in a pure tension, concrete still has the ability to transfer the tensile strength, and that is phenomena called tension stiffening. So, it helps in increasing the axial stiffness of the steel. Now, if adequate development is not provided for the ties, a brittle anchorage failure would be likely at a load below the anticipated ultimate. That's why I said, for a tie element, it is very important for you to have adequate anchorage and proper development length. So, usually you provide the 90-degree hook and of sufficient length, so that the tie is able to develop the tension force, right. That is very, very important for a successful strut-and-tie formation within a deep beam or any disturbed region. Now, this is what we said. So, we need to have anchorages and also the tension stiffening, because these are all the crack location, and between the cracks the concrete still is able to help to transfer the forces through bond, and this is how the mechanism of ties. So, and we need to make sure that the ties are adequately anchored beyond the support region by developing some hook, or if you are using very large diameter, sometimes we also weld a plate to ensure that the anchorage is provided. Okay, now let us look at, we looked at what is a strut and what is a tie. Now, let us look at the key concepts of nodes and nodal region. Again, as I told you, nodes and nodal regions are basically like a connection regions in a typical steel truss. Similarly, nodes are basically a connecting element. So, nodes are the points at which the forces in the struts and ties meet. In the strut-and-tie model, they are referred to as nodes, and the concrete in and surrounding a node is referred to as a nodal zone. So, the concrete close to that region of a node is called nodal zone. In a planar structure, typically in a 2D plane, 3 or more forces must meet at a node for the node to be in equilibrium. So, typically you will have 3 forces or minimum at least 2 forces should be there for the node to be in equilibrium. Now, for example, let us look at it. This all this yellow color are nodes, and the surrounding region is called nodal region. At these locations, you can look at the force flow. So, typically we have 3 types of generic force configurations in a node. You have compression, compression, compression node, and in all the 3 directions of joint in the node, you have compression forces, or you can have compression, compression, tension. The 2 directions you have compression, the 3rd direction you have tie. This is C, here everywhere C, compression. Then you can also have a compression, tension and tension. Now, of all these things, this is going to be strong node, and this is going to be weak, and this is going to be in between the top, right. You have more tension in the nodal region, the weaker that particular node or nodal region is going to be, right. So, you can also have rarely tension, tension, tension tie, right, depending upon the formulations of your strut-and-tie model, but the more common things are this and this. This is not common. I would say this is more uncommon. Now, let us get into the nodal zones. And you can see here, this is a nodal zone. For example, you look at here a node region where you have a CCC node, and these are the different geometries. For example, this is the width of this node that you have, LB, based on the support of the width, and this is the width of your tie element that it is coming. So, and WS is the width of the another strut. So, basically, now, prismatic compression struts are stressed in uniaxial compression, as we have explained. Now, a section that is perpendicular to the axis of a strut is acted only by compression stresses. That means basically what we are trying to tell here is, at this section you will have only compression, right. So, here perpendicular to this you will have only compression, here perpendicular to that you will have only compression. Now, if I take any section which is at a different angle, then they will have combined compression shear stress. Just like we have studied in Moore circle, in principal planes you will have only normal stresses, but if you orient the plane in different directions, you will have combinations of normal and shear stress. In the same way, perpendicular to the strut, you will have only compression stresses, but at any other angle, you will have combinations of compression and shear stresses. Now, one way of laying out nodal zones is to orient the sides of the nodes at right angles to the axis of the strut, or either to the strut or ties meeting at that particular node, and to have the same bearing pressure on each side of the node. So, that is how we design the nodal region. We try to basically orient the sides of the nodes at right angles to the axis of the struts or ties, and they also designed to have nearly the same bearing pressure as that of the each side of the node. So, that is what we are saying here. The width is chosen in such a way that the same stresses will be there. Now, there is a special condition which is called hydrostatic nodal zones, and in the case of a compression, compression, compression node, if I choose the ratio of each compression side node in the same ratio of the forces that are coming on the 3 nodes, then the stresses will become all same. So, as you know, hydrostatic stress condition, you have all 3 direction principal compressive stresses. In the same way, in this node, if you choose the dimensions in such a way that even for any load, if you get same stresses in all the 3 sides of the node, then you have a special condition called, that node is called as hydrostatic node, or that region is called hydrostatic nodal zone region. So, they are referred to as hydrostatic nodal zone because in plane stresses in the node are same in all directions, right. So, they can be extended to compression tension or compression tension node by assuming that the ties will be extended through nodal zones to be anchored on the far side by hooks or bond on the reinforcement beyond the nodal. So, you can do that as well. So, this is common for CCCC node. Now, the concept is basically we are saying that even it can happen in CCCT or CTT is by assuming that you are having an hypothetical anchored plate beyond that point where you are anchoring your tie. So, the requirement for equal stresses on all faces of the hydrostatic nodal zone tends to complicate the use of that nodal zone. So, typically it need not be having all the stresses to be same. So, this is going to actually complicate the design of such nodal zones. Now, for example, how do you find the geometry of the hydrostatic nodal zone, right? So, we see here 3 nodes are there. So, you have from reaction this, and LB is the width of the or the length of the width of the bearing plate, right. Now, you see here, and what is WT? WT is this is the tie that it is coming. So, this is the tie region. This is your width WT. Now, if you go back and this is your WS, basically what we are trying to see here is the width of this strut is going to be basically this plus this. Now, what is this? This is basically this. This location is nothing but LB sin theta. This is LB sin theta, right. Now, this is basically WT cos theta. So, the total width of this strut can be WT cos theta plus LB sin theta. So, that is what we are trying to say, this is L, right. So, the stresses are equal or close to equal on all faces of the hydrostatic nodal zone that are perpendicular to the plane of the structure, right. So, basically if this is LB, now we are trying to get this direction, and now this is the center line of your strut, okay, where the C is acting, right. So, we want to measure this width on the either side from the geometry of other considerations, right. So, the equations can be derived relating the lengths of the sides of the nodal zone to the forces in each side of the nodal zone. So, that is what we are trying to see. So, the width of this node can be written as WT cos theta plus LB into sin theta, where WS is the width of the strut, and because this is a tie element, right, that is what we say, right. And here you have again a compression bearing region. So, you can using this we can calculate your width of your strut. Now, what are the methods for formulating strut-and-tie models? There are 3 methods. Basically, the first simplest way is you do some elastic analysis using finite element package and you find the stress trajectories. If you know where the principal compressive stress and principal tension stress trajectories are there, principal compressive trajectory regions are the regions where the struts will form, and the tension regions are the regions where ties will be forming. Then the next one is the load path approach. How the loads are getting distributed will give an idea where the compression and tension elements will be forming, and then you have some standard models that have been developed over the period of time. Now, let us look at the first thing, the stress trajectories from the finite element elastic analysis. In the strut-and-tie model, again we try to get the principal stresses from elastic finite element analysis that will help to understand the force flow in the disturbed regions. So, for example, compressive stress trajectories define where the struts will form, and the tension stress trajectories will define where the ties are going to form. So, for example, again the same previous case that we looked at it, this is the tension stress in the corbel. If you look at, this is the compressive stress field in the corbel. So, when you put, like we discussed previously, this is a very nice arrangement that you can form. So, for example, you see here, this is how the compression struts are getting formed. So, basically you have one here and you have one here, right. So, and this is where we have done. So, similarly, if you look at the tie, you have something here and this entire thing is like a tie, and then you have something here. So, in this way you combine them to have this kind of things. The blue color is basically the region where you have, these are the regions where you have struts, okay, and these are the regions where you have ties. So, such kind of elastic analysis helps us to clearly visualize where we can put the compression struts and tension ties, right. So, this is one very nice way of doing it. The next one is a load path approach. It helps to visualize a force transfer through direct path between the load and support. So, finally, the load, applied loads has to go to the support, right. So, the struts again here carry compression and ties carry tension, and the nodes mark their intersections. So, typically easiest thing is to assume that angle of the strut to be about 45 degree, but you do not want to have a too steep struts as well. So, typically we put the strut in the angle anywhere from 30 to 45 to 50 degree, not more than that, right. So, it uses engineering judgment and it is aided by elastic analysis to create simplified stress analysis from the force flow point of view. For example, this is a Strut-and-tie model for a pile cap. So, you can see there is a load that is coming here, you have these two piles. So, it is the same. So, I have to create some truss. So, you can clearly say this is a strut, here there is one strut and this is a tie, okay, from 2D. Now, if I have the multiple pile caps, then inside now I am forming a 3-dimensional truss. So, again these things are all struts and they all have to be connected by these tie element. It is very simple to visualize because finally the applied load has to go to the support. So, we can directly assume how efficiently we can put the strut, but again as I have told you, the strut angle should not be too steep or too shallow, then you will end up with not a very efficient design. Now, standard models, okay, the third approach. So, usually strut-and-tie methods are widely used for design of complex reinforced concrete regions called D regions, deep beams, corbels and daptanes that we have discussed previously, and they provide template configurations for common discontinuities, helping the engineers quickly apply validated design practices for strength and serviceability. So, most of the design codes for a regular geometric discontinuity, they give you some guidelines how you can put a strut-and-tie in those regions. So, for example, simple deep beam, so it is very straightforward, strut, and tie, right. So, then you have corbel, again the compressive load has to go to the support here. So, this is a strut, so they have to be connected. So, this is a tie and this is a tie, because there is a component that has to be balanced, right. So, definitely a tie should form here and tie should form here. So, this kind of simplified guidelines are already given by some of the design guidelines that can be readily used depending upon what kind of element that we are actually designing, right. So, let us summarize what we have discussed. In this lecture, we introduced the concept of strut-and-tie model. We have described the various components of strut-and-tie model, which include struts, ties and the nodes and nodal zones, and we explained the basic concepts and also the structural behavior of the strut-and-tie model, and we also discussed the three methods for formulating the strut-and-tie model. So, in the next parts of the video, we will solve example problem and we will also design how to use the strut-and-tie method for designing the disturbed region. So, thank you.